who is Isodoro Gonzales-Adalid, that he studied for these master degrees in Madrid at the Universidad Complutense under the supervision of Victor Martin Major, and the thesis, the master thesis, was a free energy landscape in dynamical system, and he continued to study in the same group, and he wrote a PhD thesis on multifractality, exotic dynamics, scaling, and quantum phase transition in complex systems. And with this thesis, he also has got a special mention in the Paladin Prize of the last year in Florence. And we invited him to give this seminar also for this. So please, Isidoro, you can start with your presentation. And now he's postdoc in Rome, I think. Yeah, it's correct, Isidoro, in Institute of Applied Calculus, Piccone. Yeah. I don't hear you. I see your slide, but I am not able to list anything.
And now, can you hear me?
Now it's okay. Now
Okay.
I hear you for the first time. Yeah, today. Yeah,
Wow.
I asked. Okay, please, you can begin your presentation.
Okay, good afternoon, everyone, and thank you to Giuseppe and so on for the invitation to be part of these young seminars of the SIFS. Today I'm going to talk about a recent work that is still in progress, but my collaborators and I, we hope to make it available very soon in archive, but now is still in progress. This is a work that I performed joint with Massimo Bernaschi for the Consiglio Nazionale di Ricerche, Luis Antonio Fernández and Victor Martin Mayor from Universidad Complutense, and Giorgio Parisi and Federico Ricci from Sapienza University in Rome. As you can see, I'm going to talk about the Edwards-Anderson model that I'm going to briefly remember you in the following slide. But in this case, we are looking to the correlations in this system when we have a tube, and in particular, the correlation along the tube axis and the connection with this correlation with the lower critical dimension. I split the seminar in two parts, really short, theoretical introduction, okay, and then I will move to the Monte Carlo simulation, which is the main part of our work, and I will show you the results. I will finish with a slide of conclusion with the takeaways message, okay? So let's start with the theoretical introduction. And first, of course, a really brief introduction to the Edwards-Anderson model. This was proposed in the middle of the 70s by Edwards and Anderson in order to explain the behavior at low temperature of magnetic alloys. The idea is that you have a lattice, and in the node of the lattice, you have the spins, which in our case are Ising spins, so they can take only two possible values, +1 or -1. And they interact with the neighbors according to this Hamiltonian, where the coupling constant J drive the interaction. And this interaction is random along the system, but here in this talk and in the Monte Carlo simulation we perform, we consider that J have a +1 or -1 value in order to recover the ferromagnetic or antiferromagnetic interaction with equal probability. it's important to notice that you can generate so many different configurations of these couplings. Each of one is a sample of the problem that we are under consideration, and they remain unchanged for the simulation. And you need to study so many different samples in order to recover the real behavior of the system, because at the end you have this quench disorder, and you are not interested in a single one sample, but in the typical behavior of this kind of system. Associated with this randomness, we have a really root-free energy landscape. So we have so many minimas of this energy landscape. So it's difficult to the system to choose a single state. And this is normally associated with the fact that the system is frustrated because cannot choose one of these configurations. Of course, associated with this energy landscape, when we go to low temperature, we enter a glassy phase where we have a really slow dynamics, which is one of the most difficult part of studying this system, even experimentally than in simulation, that is really difficult to read thermal equilibrium due to these slow dynamics. However, one parameter that have a special role in considering this system is the spatial dimension of the system. We know that for really large dimension, for infinity dimension, we can use the mean field approximation in order to obtain an exact solution of the model. And then we can start to reduce the spatial dimension, and at some point we reach with the upper critical dimension, which is the smaller dimension where we can apply this mean field solution. In the case of the Ising Edwards-Anderson model, the value of this critical dimension is 6, okay, and is well established in the literature. Now, if we continue reducing the spatial dimension of the system, we reach the lower critical dimension, and then we lost the phase transition because it moved to 0 temperature. So the lower critical dimension is the largest one, or where we don't have a finite temperature transition. In the case of the Edwards-Anderson model, the value of this lower critical dimension seems to be close to 2.5, and there are replica symmetry breaking calculation also from numerical research that support this idea. And also from the droplet point of view, there are some works that goes in the direction that is 2.5. Okay, but what is the relation between this lower critical dimension and study the correlation of a spin glass, but in a tube? In the following slide, always we are going to see the equations in general for any dimension. Okay, but consider that our work is for d equal 3. That makes sense, and also because in the picture it's easier to show you a three-dimensional system, but moreover because we are simulating this kind of system. So now, if you consider a really long tube, the idea is that you can use a Wilsonian renormalization step in order to convert the original three-dimensional system into a one-dimensional one. So notice that the three-dimensional system is above the lower critical dimension, so we have a spin glass phase, but is governed by a one-dimensional system. So we can think in this tube as a quasi-one-dimensional system. This means, because that one dimension is under the lower critical dimension, that when we study the correlations along the axis of the tube, they must remain finite. We don't have a large correlation in this direction, going to infinity. Okay, so knowing this, we can try to study this correlation, but the first ingredient is to how to study this correlation. Probably some of you are know the trick, which is to introduce replicas of the system and calculate the overlap field. The idea is that you have the same couplings and you simulate or consider two different simulation or thermalization of the same sample, so the same couplings, which are represented by the replica A and B. And now you perform this product for each point. So you take the spin of replica A at the point X and the spin from the replica B at the point X, and this product gives you the overlap field. Moreover, we are looking to the correlations along the z-axis, so we can work directly with the overlap of the Wall plane. To do so, we use this mean of the overlap. Given the fact that we don't have infinity correlations, we can ask about the increase of the free energy for having two planes at some distance r that differ in the overlap by a factor delta Q. So the idea is to what is the increase of the free energy for having an interface between two planes at distance r. In the middle of the 90s, Franz, Parisi, and Virasoro, using the study this system in the replica symmetry breaking framework and in the large deviation region, they obtained this formula for the increase of the free energy, where you can see that it's proportional to the volume of the planes, so in this case the area, and decrease with the distance between the planes according to this power. However, it's more interested if we consider that the planes are at distance L, so we recover the idea of have a cube instead of a tube, okay? And looking to this formula, you can recognize directly this value of 5/2 or 2.5, okay, which is the lower critical dimension. The idea is that this increase in the free energy doesn't divert when we take the L to infinity for a value smaller than 2.5. So you recover the symmetry of the system and you move the transition to 0 temperature. Great, but we can go a little bit further and consider using the change in the free energy in order to introduce the probability of have this interface between the two planes. And more interestingly, we can extract how we scale the correlation length along the axis of the tube with the typical size of the base of the tube, L. And we obtain this prediction in the replica symmetry breaking framework. In our case, t is equal to 3, so we have that the numerator in this exponent is 4. So we have 4/3. Okay, but this is a prediction of the theory, and we want to test it. To do so, we use Monte Carlo simulation that I'm not going to enter in so many details and the simulation part because there are some technical aspects, but I want to give you the main problems that we have to effort and solve to study this problem. In particular, the first thing is we need to study so many different system size, L, and for each of them, we need a really large tube in order to extract the correct correlation length associated. This make really difficult to thermalize the system because a larger system more difficult to thermalize. However, thanks to that, we are in a tubular geometry. We can use the Houdayer trick, which the idea that we can construct some cluster, which are group of of spins that we can update at the same time. On the other side, there are some corrections for the result that goes to the this exponential. So you can see that we need to study really large system in order to decrease these corrections. However, we notice that instead of work with the usual periodic boundary conditions, if we take open boundary condition in the z-axis, we can reduce this correction, but we need to solve other new problem, which is the fact that the interaction in the top and bottom planes of the tube are different from the interaction in the middle. In particular, in the middle, we have 6 interactions, but in the borders, we have only 5, which is a problem from the algorithmic point of view. Here I show you for a periodic boundary condition system, really large, you can see 512, some of the cluster, the Houdayer cluster that we obtain in the system. You can see that there are regions that belong to the same cluster, so we can update all the spins in the same cluster at the same time. But the good thing is that if you know something about this cluster algorithm, that is that in three-dimensional, in a three-dimensional system, normally the cluster cover all the system. So given the symmetry of the problem, it's not useful to perform this update. However, here, due to the fact that we have this tube, we don't have this percolation, so the cluster are large, but doesn't cover the whole system, making faster your thermalization. To convince you that we can do faster than the usual way, here I show you the evolution along a simulation of the square of the overlap. In the bottom data, you can see a simulation where we use the usual parallel tempering technique to thermalize the system. And in the upper part, we use the parallel tempering and this Houdayer trick or Houdayer move. And you can see that we reach a plateau, which means that we are this sample is thermalized. And you can see that it's much faster. Moving to the problem of the open boundary conditions, as I said before, we have that in the middle of the tube, the interaction of the H spins are 6. But when we move to the upper side, the upper bound, for example, we have only 5. But we decided to introduce a new interaction along the y direction in order to recover the 6 interaction. The idea is that you can use exactly the same algorithm or the same detailed algorithm in how you update the spins, how you measure the energy, because you have exactly the same number of interaction. However, when you are going to measure something, you have to measure far away from the boundaries to be sure that you don't have a boundary effect in your measures. However, in order to check that this gives you the correct result, it's better to take a look directly to the data. And here I show you the correlation function of this overlap between planes for a system of linear side 16 in the transversal direction. And with periodic boundary conditions, we have to consider a system which has a tube of length 512, but for open boundary conditions, the length of the tube is only 48. So notice that it's more than a factor 10 in the side in this direction, making much easier to thermalize the open boundary system. However, the data are perfectly compatible in the error. So this must convince you that using this open boundary condition, we can obtain the same result. If this is not enough, we can directly extract the correlation length under consideration from this correlation, and you can see that the data obtained from the open boundary system and the periodic boundary system are compatible in the errors. These errors are errors over the samples because, as I said before, we have to simulate so many samples to study the typical behavior of this system. Okay, so now we move to the main part, which is, okay, we have a prediction, which here the numerator is 4, and we can simulate a system of size L equal 8, 12, 16, and 24, and compare your data with the prediction. You can see that for t point equal 0.7, which is inside the glassy phase, because the critical point is at 1.1 or close to 1.1, we recover, or we have exactly this behavior of the scaling of the correlation length. We also include the data close to the critical point where we expect this linear behavior. So let me conclude with a brief summary, which to put everything together, which is say that using our Monte Carlo simulation of this three-dimensional tube, we can obtain a result that is compatible with the replica symmetry breaking prediction. This is thanks to the fact that we can introduce in this tubular geometry and use the Houdayer trick or the Houdayer move, and also with the fact that we can use these open boundary conditions to study really large systems. However, mention that we need more than 400,000 GPU hours to collect the data to obtain this last plot. There are also some questions that we expect to answer or in future works, which is the effect of the temperature, or more interesting is the fact that instead of study the correlation of odd operator of the overlap, we can study the correlation for even operators like the square of the overlap field. And in this situation, the prediction of the replica symmetry breaking framework and the droplet framework are different. So we expect to make a step forward in order to establish what is the theory more close to the real situation in the behavior of this system. Here you have the reference I include in the slide for if someone wants to check them in late. And also, if you are interested, you can ask me and I will share with you the slide for reference. So please, if someone is interested, contact me. And this is all, and thank you for your attention. If you have any question, I will really happy to try to answer them.
Okay, thank you a lot, Isidoro, for this very clear talk. I think we have one question, please.
Yes, I have a question. So due to this tubular geometry, is there any correction on the critical exponents?
You say correction in the critical exponent?
Yes, I mean, we know the numerically the critical exponent in three-dimensional EA model, but since you are considering this tubular geometry, are there corrections on the critical exponents?
But you are thinking in the fact that, of course, there are some corrections, but the critical exponents will be in the critical point. But we are talking inside the glassy phase.
Okay, so you are not looking across the phase transition, you mean?
when we are talking about this line, yes.
Okay.
But the idea we include for the value for consistency to say, but the main result is inside the spin glass phase. So this is why we want to check this prediction in particular, which is inside the spin glass.
Okay. Yeah, just one more small question. So does this Houdayer trick also work at very low temperature? Suppose the temperature is 0.2 or 0.3. Does this Houdayer trick works?
The problem is that deep you go in the spin glass phase, longer must be the simulation, or in other words, more difficult is to thermalize the system. So if you try to go for 0.5 or 0.4, something like that, probably you cannot extract the correct correlation length, because you cannot thermalize this, even thermalize the system. So you cannot start to study the equilibrium. In particular, I don't remember the exact number, but I think that one of the deepest number I remember from the Janus collaboration, which is one of the ones that go more deep inside the spin glass phase. I don't know if someone can correct me, but I think it's something like 0.6. Go further makes much difficult to thermalize the system. So at the end, you cannot measure anything in the, you only can study the dynamics, because the static is not, you cannot reach equilibrium.
Yes, I agree. But I mean, I was thinking whether this Houdayer trick in tubular geometry gives some advantage, because you are in the tubular geometry and you are saying that this Houdayer trick is advantageous. So maybe, I mean, we can go to the deeper temperatures faster than the simple parallel tempering.
Will be possible, but the same. One of the problems, when you perform the parallel tempering at the end, if the dynamics in the lowest temperature is frozen, it's affect to the whole range of temperature. You can try, given the fact that we use the Houdayer tricks and the open boundary condition allow you to study a smaller system. Of course, this make everything easier, but at the end, go really deep inside the spin glass phase is not easy from the computational point of view. Will be really good to have access to this. Other problem will be, okay, we talk about the cluster of the Houdayer move. So imagine you move a little bit inside the spin glass phase, so you go to 0.6, and now the cluster grows a lot. So you have only one really large cluster, okay, and some is really small. When you try to use this Houdayer trick, you have the problem that in some sense you percolate. So the Houdayer trick is useless. So, and we also study the effect of the temperature in the side of the cluster, and it's not easy. Even with this trick of the cluster move, the open boundary condition, and so on. Will be really good to go deeper, of course, but it's not easy from the computational point of view.
Okay, thank you so much.
Isidoro, when you say not easy from the computational point of view, can you say something more about this? For example, the amount of CPU hours you use, some details about your simulation.
For example, to say something, we try to go a little bit further, and to generate to study a system of linear size L equal 32. Okay, so say put one more point here, okay, in this plot, and after something like 2 months of running continuously over a cluster with something like 100 GPUs.
100 GPUs.
We don't reach the thermal equilibrium.
So it's really a lot, yeah.
Yeah, so when I say more than 400,000 GPU hours, it's real. We make the count. We know how many GPUs we have, how many months we run, and I say going a little bit more further will be really difficult.
Okay. Other comments? Yeah. I don't see other hands
Okay.
in the list of participants, so I think we can thank again the two very guest speakers of today, Isidoro and Juliette, and thank you to all participants also. And I think we can clap to everyone. And with Federico, we say bye-bye to everyone, okay?
Bye.
Ciao.
Bye-bye.
Ciao.
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 Ciao a tutti.
Ciao.
Ciao a tutti.
Ciao.
Ciao. Ciao.